With the foundation that we gained in the last video lecture on statistical decision theory, we now have the foundation we need to start solving some real problems. And we'll do this using what are known as Bayes classifiers. They're also called discriminant analyzers, or it's called discriminant analysis for historical reasons, because we discriminate one class from another. Okay, we're going to look at two types of discriminant analyses, quadratic and linear. So let's formulate the discriminant analysis problem. And basically, this is a classification problem, as we said, and we can consider script G to be the set of classes where there are k classes in this set. And capital G then is the choice from that class. So for example, in the admission decision for a university, it would be waitlist, deny, admit, 3 classes. Those would be the classes in script G, and capital G would be a selection from that. We could have diseases or choices of diseases, a cold, a flu, allergies, or none, and that would be our choices for doing a diagnosis, for instance. Now we also have data for a number of students who want to be admitted to the university, for instance, or a number of patients. So there's n of those, and we have variables that we're measuring on each one of those students or those patients. For instance, GRE tests of different types, GPA values, and so forth. And we've got medical tests, lab tests that we can take for the patients, and measurements that we can take. That then forms a matrix. This is an n by p matrix, and we call it the data matrix. Okay, from what we've learned in statistical decision theory, we know that the Bayes optimal decision is made by minimizing the Bayes risk, or this expected loss function. And we know that the solution to that is by choosing the class that has the most likely posterior distribution. And that's what we've written here in this inequality. So among all classes, we're going to select class I. That's one of those selections from admission or one of those selections from the disease categories. We're going to select it, given the data, if it's greater than the posterior for all other classes. And we'll break ties arbitrarily. If it turns out there's a tie between these probabilities, then we can just flip a coin or do some other randomization. Now, from Bayes' rule, we know that we can rewrite this inequality because what we've got are posteriors on either side of the inequality in inequality 1. And we can rewrite that in terms of the likelihood of the data given the particular class times the probability of the class. And that's all we've done in inequality 2, is we've just applied Bayes' rule and rewritten each side in terms of the likelihood and the prior. Now we can rewrite it again, and it's typically shown this way as a ratio. This is called a likelihood ratio. And what we've done is we put the likelihoods on one side and the priors on the other side of the inequality. So we can see then that the choice, the GI choice, is on the left-hand side as the numerator of the likelihood, and on the right-hand side is the denominator of the priors. Now, the question is, how do we do this? And the way that we do it, again, comes back to this notion of where do we get priors from, for example. Typically, we get the priors from the data. And the likelihood function, so in other words, we look at, in the case of the disease category, the base rate. How many of this particular disease do we see in the population? And that's our prior distribution for it. Same thing for admissions. Okay, we typically look at these base rates as we talked about when we discussed priors before. The likelihood typically comes from a number of places. One is we can assume its form, we can assume it's a Gaussian, and that's what we're going to do in this video. We can also use a distributional fit, and we'll do that in a later video. Or we can do a combination of these two. Basically, I will say this. What we're doing today provides a solid framework for you to modify at any point given the data and the form of the problem that you have to solve. This is a very powerful framework that we're giving you for problem solving using Bayesian methods in this video. Okay, so let's assume then that we have a multivariate Gaussian distribution for the likelihood. And again, we can now look at the Bayes optimal decision rule given that. So the likelihood then is in the form of a multivariate Gaussian, which is what we show here. And in this case, let's just recall that these capital sigmas are the variance-covariance matrix for the particular class. So in other words, in this case, we have sigma j. Let's say that's for the group of students who we deny admission to. We'd have another sigma I that would be the group of students that we admit, and so forth. Same thing for, again, the medical problem. It would be each one of the individual classes would have its own variance-covariance matrix. And each one of the individual classes would have its own mean vector. It would be the location of all the tests. Okay, so in other words, the GRE scores for that particular group of students and their GPA, or the test results, the lab test results for that particular group of patients with that particular disease would be defining that mean vector, and of course the variance-covariance matrix as well for that particular class. Okay, this is going to give us what's called a quadratic solution, and we'll see that when we actually formulate the solution. So we can now look at the Bayes optimal decision rule using what we saw before. And basically it says we're going to choose among all the different classes that we can choose from. The one we're going to choose is the one for which this likelihood ratio, as we saw before, is greater than the prior ratio as we've defined it. So, and now all we've done is we've taken those Gaussian likelihoods and just plugged them into this this inequality that we saw before, which was the Bayes optimal decision rule. And now what we do is we just take a log of each side, and then we get some cancellation of terms, and it turns out that what we're left with is basically a difference of the determinants in front of the log of the determinants of the two variance-covariance matrices, but more importantly, and that effectively provides what amounts to a constant term in the solution. But more importantly, what we find is when we're solving for these x's, the solution is quadratic, and we see that because the two terms that are shown here are quadratic. They're squared terms in x's. So the solution then is going to be the solution to a quadratic equation. And in two dimensions, we can visualize that as the way we normally visualize solutions to quadratic equations, which are the conic sections. So they'll show up as a parabola or a hyperbola or an ellipse. These are the kinds of things that we would expect to see in two dimensions. And that's what we'll visualize when we look at this next example. So in this example, let's consider a case where we've got a mean vector for our first class, which is at the origin, and for our second class, which is slightly off the origin on the y-axis. Okay, and the variance covariances are as shown. in the case of the first class, we have a lot more variance around the first dimension, let's call it the x dimension, and in the second class, we have it around the second dimension. The variance is higher on the second dimension, or the y dimension, if you will. And we can start with equal priors, and then we'll look at the case where the probability of the first class is quite a bit less. In fact, the second class is 9 times as likely as the first class. Okay? So two different cases. So if you think about, let's say, a problem where we're trying to decide to give someone a loan or not give them a loan, or give them a credit card or don't give them a credit card. Well, then we've got equal priors in the first case, and in the second case, the likelihood of, let's say, not giving them the credit card is 9 times what it would be for giving them a credit card. Okay, for the equal prior case, we have our two classes, and again, one of the classes, the blue class in this case, is the one that has the greatest variance on the first dimension, okay, the x1 dimension, and And the orange class is the greatest variance in the x2 dimension. And what's shown here is the solution, again, to that quadratic, and that the solution in this case turns out to be a hyperbola. And it's got two decision lines defined by that hyperbola. One, so in other words, if you're above the first of those decision lines, you select orange. And it turns out if you're below the second of those two, you also select orange. The only time you're going to say that it's class blue is when you're between the two. Okay? So it may be a little bit counterintuitive to see why we select orange when it's below that second line. But if you think about it a little bit, what's happening is that that blue class is it's very tight around the x1 dimension, whereas the orange class is very tight in the I'm sorry, I said the first class is very tight in the x2 dimension. It's got less variance in x2, a lot of variance in x1. The orange class, on the other hand, has a lot of variance in x2 and less in x1. And that increased variance in x2 means that eventually it pushes out from under the blue class in the x2 dimension and becomes much more likely as the values get lower and lower in x2. And that's why we select down there. So this is an example of a quadratic solution, and this is a quadratic discriminant function. In the case where the priors are not equal, we get a solution that turns out to be a hyperbola. But it is in this case that the solution is we're going to pick orange if it's between these two hyperbola, and within that region between them, we pick orange. So it goes right through the center of the blue, and we still are picking orange because it's more likely. The priors are saying it's much more likely to occur. And the only time we pick blue is when it's on the outside, either the outside left or the outside right. That's the only time we pick the blue solution. Think about these examples and how this quadratic works and how these quadratic solutions define the decision lines that we get in order to decide between the classes. Okay, let's now look at the linear case. And in the linear case, what we do is we again assume multivariate Gaussian distributions for the likelihood. The only difference now is we're going to assume that the variance-covariance matrix between all the classes are equal. So in other words, if we think of our admission problem, then each one of the admission classes, admit, deny, wait list, they all have the same variance-covariance matrix. Or if we think of the disease one, every one of the disease categories, flu, cold, etc., they all have the same variance-covariance matrix. The only thing that's going to change is the mean values. Okay, so our decision rule, again, using what we learned from statistical decision theory, the Bayes optimal decision rule is given by this ratio of the likelihoods, and that's all we've done is we've put the likelihoods again in that ratio. In this case, though, notice that we have no subscript on the sigmas. It's gone because the sigmas are all equal. The variance-covariance matrices are all equal. So the only thing that's changing then are the mu's, the mean vector for each of the likelihoods that we have. That's the only thing that's changing. And when we solve this, it turns out that what we get is we get a linear equation in x, and then what amounts to a constant that's represented by the two terms in the mu's and sigmas. That's basically just forms a constant because we know those values. We just solve for them and produce the constant value, the scalar value that's the result. On the other hand, the first term in that on the right-hand side of that inequality is a linear function of x's, and so we're going to get a linear solution to this discriminant problem. And here it is. And notice in this case, when we look at the two classes, the blue and orange classes, that they have exactly the same variance-covariance matrix. So they look essentially the same in terms of their variance-covariance structure. The only thing that's different between them is the mean vector, the center point of each of those two bivariate Gaussian distributions. And the line running between them represents the linear discriminant that separates them. So if you're above that line, you pick orange. If you're below that line, you pick blue. If we look at unequal priors, in other words, if the orange class becomes more likely, let's say it was 9 times more likely, then notice that what happens is the linear separator between the two classes just moves closer to the center of blue. So in other words, we're more likely to pick orange. It's just telling us pick orange more times than you're going to pick blue. It's also possible to just ignore the differences in the variances, variance-covariance matrices, and treat the problem as if it is as if they have equal variances. And this is often done, and this is what would happen if we did it in our first case, where we showed that they were quite different, but we could still get a linear solution. And the reason that we show this is because in practice, it turns out that the linear solution is often much better than the quadratic solution. The quadratic solution has a tendency to overfit in many practical problems. And the linear solution, the simpler solution, turns out to give a better answer for many real problems than the quadratic solution. So you should always try this linear solution, even when you know that you've got quite different variance-covariance matrices. Always try the linear solution and see how well it works in practice. Okay, one more topic that we'll look at, and that's the cost of misclassification. And this is a nice thing about discriminant analysis and the results we got from statistical decision theory is we can handle a case where the cost of choosing a class is quite different. And so, for example, let's add some notation here. We're going to let CIK be the cost of choosing class I. So that's the class we say the data come from, when actually the true class is K. We can easily use what we learned from statistical decision theory and the ideas of Bayes optimality. Again, the Bayes optimal solution is the one that minimizes this expected loss. In this case, the expected loss is given by these cost functions. And we're going to choose the class, GI, let's say, that minimizes that expected loss. And that's the one we will pick. Okay? So of all the ones, we will pick class I that minimizes that loss. And you can see that when you look at this inequality. Notice that the subscript on the C, it's the one that we choose. It's saying we choose, if you look on the left, it's saying we choose class I when the row class is K times the probability that it's of class K. Okay, and we're gonna do that over all of the classes. So each one of the classes will take it, which is going to give us our expected loss. And that choice of I then has got to be better than the choice of J for all other J's, for all other class labels. It's got to be better than that. So it's telling us pick the class that has the lowest expected loss. And again, we can break ties arbitrarily. Okay, it's often the case that we say that if you get it right, so in other words, if I pick class I, so if I say it is this disease and it actually is the disease in the data, then my loss, my cost is 0. And that's typically what we do. But think about the fact that there may be some cases where we don't want to do that. We in fact may want to not do it. And to just get you so that you can think about it, because students often have a hard time thinking of examples, the problem here is the name cost. So what you should think about is that instead of thinking about this notion of the cost of getting it right as what you're looking for, think about it as the reward. And that means that the cost goes negative, okay? So in other words, you're going to reward yourself. So if there's a particularly bad disease, virulent disease that you want to get right, among all other diseases, then you could reward yourself and give yourself a negative cost for that. Or if there's a particular, let's say, investment that you're looking at that you really want to get right, you could reward yourself for that. Notice that in contrast, the idea of this differential cost is important because it's the case that in some problems, the cost of misclassification is clearly not the same. So in other words, if I were to say, for instance, that somebody has a disease when they don't, okay, they don't have the disease, versus I tell someone that they don't have the disease when they do, those costs are often quite different. The latter, what's called a false negative, I tell somebody that they don't have it when they do, is often it's a much higher cost because now that person can go out and infect people. Or if it's something like cancer, then they don't get treatment because we misdiagnosed them. We didn't think that they had it when they did. So there's a very high cost for this false negative. And in medicine, typically it's the case that we try and absolutely minimize false negatives. We try and make it so that we make that absolutely zero, which means we impose a very high cost on false negatives as opposed to false positives. Okay, so to see how this gets set up, suppose we have only two classes in this case, and we'll assume for our purposes that the cost of getting it right is zero. So in other words, there's no extra reward for a particular class. And again, we can apply our notions of Bayes optimality using Bayes' rule to get the likelihood ratio. And here's what it looks like. It's a simple rewrite of the likelihood ratio. And in this case, notice that we've got the costs on the right-hand side now with the priors. This is very convenient because it allows us to quickly see how these costs work with the prior distributions to change where that discriminant line goes, or there's discriminant lines in the case of a quadratic solution. It's really easy to see for linear discriminants. Okay, for linear discriminants, it's this nice ratio on the right-hand side. It's the log of the costs and the prior probabilities. And you could think about it this way. If you've got let's say a condition or disease that's a very low likelihood in the population, so its prior is very, very low, but the cost, as we said before, of getting it, of misclassifying it is very high, then what that does is that even though the probability of that particular condition may be very, very low, since the cost of misclassifying is very high, it moves that discriminant surface more towards allowing you to correctly classify or to classify that particular condition than not. So you're definitely going to be more likely to get, let's say, false positives, but you're not going to miss these particular problems. And that's what that cost ratio does in this particular case, in these discriminant functions. Okay, next time we'll look at additional extensions to these notions of Bayes classification.